There we are. Okay, good. So today's lecture will be lecture 6, Attitude Representations, part 2. As a reminder, last class was lecture 5, Attitude Representations, part 1. And so we tried to answer this question, which was, which way is the camera facing? Or what is the spacecraft's attitude? And the right question to ask is, in reference to what? And so if you know that there's some world frame, and we'll often use the International Celestial Reference Frame as our world frame, you might call that an inertial frame. And then you might have some spacecraft body frame shown here in green, or some camera frame shown here in blue. The relationship between some frame and some other frame is a rotation. And we talked about a couple of different ways to describe those rotations, but one of the key things that I was hoping y'all would take away from the last lecture is that you can describe that rotation many ways, and it's like learning how to say the same sentence in many different languages, right? So you can pull out your Spanish to English pocket reference guide and then convert from one to the other. It's the content that we're after, right? So the content, there are 3 degrees of freedom describing the rotation from one frame to another, and we're trying to get that content across in a number of ways. And so you might remember we are going to go over, or already did, 4 different ways of discussing attitude and the kind of issues and considerations that go along with those. The first is attitude transformation matrices, which is your classic 3x3 matrix. We went through some very simple examples of how to build those from scratch, and then really hammering home the idea that active and passive rotations are 2 different things. A rotation matrix and an attitude transformation matrix are not only different, they're actually opposites of each other. And then the next thing that we got into was Euler angles, and kind of the first you rotate about the x-axis, then you rotate about the y-axis, then you rotate about the z-axis. So this series of 3 rotations is the Euler angles, and people will often call those yaw, pitch, and roll. If we're talking about z-axis rotation, would be a yaw, x-axis rotation would be a roll, y-axis rotation would be a pitch. And so if you're going to do a z-axis and then a y-axis and then an x-axis rotation in sequence, that would be a yaw, pitch, roll sequence, or a z-y-x sequence, or a 3-2-1 sequence. We might remember that the sequence that gets us from the Newtonian frame to the parafocal reference frame all the way back in orbital mechanics, lecture 4, was a 3-1-3 or a zxz rotation. And then finally, we talked a little bit about, how ugly the matrices get when you actually try to multiply these out. And so at the end, I left off on kind of a cliffhanger. If you use Euler angles, or if you use attitude transformation matrices, or if you use angle vectors, which we didn't get to yet, today we're going to talk about angle vectors, sometimes called Euler axis angle, which is a bit confusing because then there's Euler angles, which is different. And then also the unit quaternion being used to describe a spacecraft attitude or any body attitude. That's going to be our main focus today. And looking at my notes, we are going to have a little bit less content today than yesterday, which makes me think that we won't use the full hour and 20 minutes, hour and a half. And what we'll probably do is spend all the extra time either asking like open questions about Q&A, or open questions about the homework 1, or if we want, I can give like a quick primer on using numerical integrators like ODE 4.5 and RKF 4.5. I think most of y'all are experienced with those by now, but we can chat about that briefly if you want. Any questions about the content on lecture 5 before we move on, or we're feeling okay? All right, we left off on a cliffhanger, and I said, beware gimbal lock. And so that's actually how we're going to start today. We're going to start by talking about gimbal lock. So anybody who's feeling brave or just wants to get their question answering done with so that I don't ask a harder question later, does anybody know what gimbal lock is? Or have you heard of gimbal lock before? Does that mean anything to you?
Is it when 2 rotation axes align and then you can't tell which axis you're actually rotating about?
Very good. I can't see on my screen who just piped up. What's your name?
Jacob?
Jacob. Oh, fantastic work on that, Jacob. Yeah, so you're right. But now I got to ask you a follow-up question. So you said 2 of your rotation axes line up, So that's kind of like if your yaw and your pitch axis, something like that, line up, then you can no longer determine the angle corresponding to each of those two axes, essentially, which is absolutely correct. So let me ask you this follow-up question. Is that like a physical phenomenon? Is that like a device like breaking, something you could hold in your hands doesn't work anymore because of gimbal lock? Or is gimbal lock a mathematical phenomenon, something where we're going to have problems with our equations now?
Combination of both.
I tried to trick you. You're too good. Okay, very nice. It is both of those things. Okay, very good. So, wow. All right, you are on top of your game today. So I'm going to start with a diagram here, just to kind of illustrate what we're going to be talking about today. I'm going to start with drawing the Apollo Command and Service Module, which of course looked like this. There you go. So, and then we're going to have a little hole in the side, and then you've got smoke coming out of it because this was discussed in the movie Apollo 13. So, right after the explosion, the venting gases caused the spacecraft to start spinning wildly out of control, right? And they had to get it back under control. And they had all sorts of issues for the rest of the mission. And they mentioned this specifically. There's one scene in the movie where I believe Mission Control actually says that the Apollo 13 astronauts are dancing with gimbal lock. And what they mean by that is, we kind of do a little arrow here, that there's a physical device inside the spacecraft called a gimbal. And we're going to talk about, we have a whole unit on inertial navigation. We're going to talk about gyros and gimbals and measuring your attitude and so on and so forth. That's coming up later. And let's say that we have this going on, and then in here we have something that looks like this. Right. So what it is a series of rings that each allow the inner ring to spin along one axis. And those axes start to kind of sound a little bit like roll, pitch, and yaw, right? And so you've got three ring gyro in the Apollo command module. And the issue that you're running into is if two of these rings line up with each other, which will happen at some attitude. Now the question is, okay, once those two are aligned, first of all, they're stuck now, like they're physically stuck, right? And that would mean that something that you could hold in your hands is now broken. You need to get in there and fix it. But also what happens is it becomes impossible mathematically to determine the angle corresponding to either one of the two rings because they're lined up with one another. And so you've got a mathematical problem and a physical problem happening at the exact same attitude. And so then here's another fun engineering question for you. Why not use a four-ring gyro where this isn't a problem? Why didn't Apollo use a four-ring gyro? And for reference, Gemini used a four-ring gyro where this isn't a problem. So why did Apollo use a three-ring gyro? Any ideas?
Is it because adding another ring would add another degree of freedom?
Ah, very interesting. So your attitude still only has 3 degrees of freedom. So adding another ring, it gives you another measurement, but it's a redundant measurement. So if you have more measurements than degrees of freedom, that's okay. That's not a huge issue. It's if you have more degrees of freedom than measurements, then we start to have an issue. So that's a good idea, but not quite. Any other takers on why use a 3-ring gyro on Apollo rather than the 4-ring gyro they used on Gemini?
If you add another ring, it's more complicated. And I'm guessing there's probably some computation going around with these measurements. And I know that the Apollo program, because it was so early, it just had like very low computing power. So was
Ooh,
computing
you're
power
extremely close. You're extremely close, but that's still not quite it. Because remember, the Apollo program was very simple. Like the computer that it ran on was very primitive by today's standards, but it was still worlds ahead of Gemini, and Gemini had no trouble running a 4-ring gyro. But you're very close, though. You said it's too complicated, but then you went off in a computer science direction, and I'm thinking of something else. Do you want to try again, or maybe not?
I'm not really. I don't know what else.
Yeah. See, this is one of those thought experiments that teaches you to think like an engineer instead of a student or grad student or mathematician or dynamicist. The answer was money. They didn't feel like spending the money for a four-ring gyro, so they ran into this problem. And actually, it's even worse than that. The people that worked on Gemini talked to the people that worked on Apollo. It was not the same company. NASA hired different contractors. And the people who worked on Apollo were like, yeah, all right, thanks, Gramps. We got it. We don't need your help anymore. Got it. Cool. Thank you. We're going to work with the three-ring gyro. Bye. And the folks that worked on Gemini were pleading with them, like, just use the four-ring. It's worth the money, please. And they didn't feel like it. It was different contractors, and they said, don't step on my toes. Don't tell me what to do. And they made that choice. So that's one of the things that I've learned since I've started working, is that a shocking number of decisions are not made based on mathematics. Most of them are made based on economics, and some of them are made completely arbitrarily, and you just need to learn to live with it. So that was learning things like that was a bit of a wake up call for me coming out of graduate school, where it's like, but surely they know about degrees of freedom. It's like they don't, and they don't care, and they're in charge of the money, and you're not. Have fun. So that was kind of a wake up call. But anyway, I want to circle back to the academic idea here, which is gimbal lock. So we're going to be discussing gimbal lock, which is a kind of a physical phenomenon, and then the mathematical phenomenon of singularity. And that's not the singularity that happens at the middle of a black hole. It's a different singularity. So here comes the writing portion of our lecture here. So Euler angles, which is what we discussed at the end of last class, make intuitive sense. Intuitive sense. And are often the first method, or one of the first methods, of attitude representation. Taught to students. Now, we have an issue here, and this is a mathematical issue, is that members of the special orthogonal group 3, SO3, which includes attitude transformation matrices, SO3 as a group has no global three-component representation without singular points. So what that means is that gimbal lock is an issue with Euler angles. It is also an issue with attitude transformation matrices. It is also an issue with angle vectors. As a matter of fact, we're only going to learn one method of attitude determination or attitude description, which does not ever fall victim to gimbal lock. So we'll get to that in a little bit later. In plain English, whenever you choose a three-component attitude representation, you are, like in the movie, dancing with gimbal lock. So the simplest way to describe an attitude singularity that I can think of is to use a metaphor, use a different type of singularity, right? So here is a question. I'll take a volunteer, and it's going to need to be a brave volunteer who does not know the question yet, but it should be relatively straightforward to answer. Who's feeling brave, wants to get their question out of the way today?
I'll go for it.
All right, here it goes. If you were standing at Earth's North Pole, what is the latitude of the North Pole?
90 north.
Cool. What is the longitude of the North Pole?
Yes.
You found the problem. It's every longitude is a valid answer at the North Pole, right? And so what we run into is there are attitude representations where one of your angles, roll, pitch, or yaw, becomes meaningless because every angle would get you there. And that's no good because if there's an infinite number of solutions, there's no unique solution, right? That's just as bad. Like when everyone's super, no one is, right? Same idea. An infinite number of solutions is bad. We want there to be a unique solution. So thank you, Max. That was good. So that's same idea here. There exists, and by the way, this backwards E is a mathematical symbol for there exists, which I write when I'm feeling a bit lazy. There exist singular points which can be expressed by an infinite number of rotations. Same idea. And then same thing we were talking about before. Attitude singularities occur mathematically and physically at the same point or points. There can be two. So suppose we have a spacecraft with a 3-axis gimbal, like the one that we just talked before, right? Suppose a spacecraft has a 3-axis gimbal to measure its attitude with respect to, that's WRT, with respect to inertial space. And we'll talk a bit more about how these gimbals work. We have a unit on inertial navigation that is coming up. Suppose then, and then suppose axis 3 becomes aligned with axis 1. And so, and this occurs whenever theta 2 equals 90 degrees. So the angle of the second axis is 90 degrees. So you can just imagine, however you've got axis 1 oriented, axis 2, if it is spun 90 degrees with respect to axis 1, will now align axis 3. So essentially, it's the same as two of these rings being lined up. Actually, as drawn, this is in gimbal lock. So you've got ring 3 and ring 2, or sorry, the outer one is ring 1, and these are aligned. And that causes frowns. Right? So, because whenever that happens, it becomes impossible to tell how much ring 3 has spun and how much ring 1 has spun. Because they're aligned, only the sum of their two angles can be measured, right? And so you could think of it this way. In this case, that axis 3 and axis 1 are lined up. In this case, a rotation about axis 3, or sorry, axis 1 or 3 produces the same motion overall. Therefore, that's what these 3 dots are. Therefore, it is impossible to know either angle. Right. Now, let's see what happens to our yaw pitch roll matrix from last class when theta 2 is 90 degrees. So just as a reminder, and here I'm going to tab back to this in a second, we had this big ugly matrix at the end of lecture 5, which is our yaw pitch roll matrix, which looks like this. And if we know that we have theta 2 is 90 degrees, then that means all of our C2s are going to be 0, right? Because cosine of 90 is 0. And all of our S2s are going to be 1, right? Because sine of 90 is 1. And so what happens then, I'm going to call this T, and it's a yaw pitch roll. So actually, I think they should say ZYX. Do I have this backwards in my lecture notes? Yes, I do have this backwards in my lecture notes. Sorry, it's just on my piece of paper, I have this backwards. I want to be consistent. T, ZYX, gimbal lock is equal to, and just we'll skip all the pain and suffering, go right to the answer here. 0, 0, -1. And over here we have cosine 1 sine 3 minus cosine 3 sine 1, cosine 1 cosine 3 plus sine 1 sine 3, 0. Sine 1 sine 3 plus cosine 1 cosine 3, cosine 3 sine 1 minus cosine 1 sine 3, 0. And this, you might need to stare at it for a little bit to convince yourself, is a singular matrix. And remember, a singular matrix, here, remember, a singular matrix is what's said to be called is rank deficient, non-invertible. So we can't undo this rotation, right? There's no way to invert it. And we cannot recover theta 1 and theta 3. And so because of that, we're kind of sunk. And that's a problem that we have to watch out for. Now, one solution to this, well, basically the solution to this is to use a different method of measuring attitude. So we can get away from this if we use physical devices that measure our attitude that are not 3-ring gyros. So 3-ring gyros will run into this. But we will still have this problem mathematically as long as we're using any of these, 3 degree of freedom, Euler angles, that sort of thing. What we need to be moving in the direction of is something that has 4 degrees of freedom. So actually, now that I think about it, it might have made sense to go over gimbal lock after angle vectors, but c'est la vie. We're going to talk about angle vectors now, which is another 3-parameter representation, which is very nice and convenient, and you will probably use it in this class at some point, but it is also subject to this issue. But before we move on from gimbal lock, any questions about that? So far, so good? All right, so next is what I call angle vectors, and which is also sometimes referred to as the Euler axis angle. There's already something called Euler angles, so I feel like Euler axis angle is a bit confusing, so I'm going to call it angle vectors. All right, so moving on to a different discussion point here. Euler's theorem, which we're actually going to talk about in a minute. And that's not to be confused with Euler's equation or Euler's formula. There are so many things named after Leonard Euler. I don't know how we can keep track of all of them. Euler has a theorem which dictates that remember, we know that any attitude or any rotation can be broken down into 3 rotations about either body fixed or space fixed directions. It's also true that any 3D rotation or any even more complicated rotation can be expressed as a single rotation about a fixed axis by some angle, hence the Euler axis angle. So now we're not saying what's the roll, what's the pitch, and what's the yaw to get from before to after. Now we're saying what's the axis and what's the angle. Now you can imagine, and we're going to kind of visualize this, by necessity, points lying on the axis will appear the same in the initial and final frames. So you can imagine this. If you have any shape, you can just say a potato, right? Let's say that you have a potato, and don't try this at home because it's going to make a mess, and you stab a pencil through your potato, and then you hold the pencil by either end with your thumb and your forefinger at either end of the pencil. You can then twist that. You can orient the pencil, before you stab it through the potato any way you like. That's your axis. And then you can twist it, and that's your angle. And you can get the potato from any orientation to any other orientation by doing that. And you can imagine then that the pencil itself looks the same before and after, right? By necessity, because you didn't twist the pencil around. You jam it through once, and then you spin about the pencil. And so all of the points on the potato that lie along the axis of rotation are going to look the same before and after, right? So we can actually go through the exercise of proving this. Why don't we? Let's go through the exercise of proving this. So let T be an attitude transformation matrix, which is kind of our bread and butter for describing an attitude. And what do we remember? We know that T inverse is the same as T transpose. We also know that the determinant of T is 1, which is another way of saying it's a pure rotation. There's no scaling, there's no stretching, there's no shrinking. This 3x3 matrix has a determinant that is exactly equal to 1. And then by necessity then, the determinant of T inverse, which is the same as the determinant of T transpose, has to also be equal to 1, because undoing the rotation still doesn't scale or stretch or shrink it. It's still going to have a determinant of 1. Also, the determinant of the identity matrix, which we talked about before, is 1 as well. Okay, those are all the things that we know beforehand. So here comes our derivation. Derivation is a strong word. The determinant of T minus the determinant of I is equal to 0, which is really to say 1 minus 1 equals 0. Okay, hopefully everybody's convinced about that so far. Now here comes the sleight of hand. This means that the determinant of T minus I has to then also be 0. And then it must be the case, by the law of matrix math, that the determinant of T minus I transpose has to also be 0, because if you take the transpose of a matrix, that doesn't change its determinant, right? Now you can actually distribute this, right? So this is the same thing as saying that the determinant of T transpose minus I transpose, well, I transpose is just the same as it is to begin with, is still 0. So put a little bit more simply, this is saying the determinant of T transpose minus I, right? Because I transpose is just itself, is 0. Okay, we're getting there, not quite done yet. Hopefully this all checks out so far. Next, we're going to be a little bit cheeky. We're going to say the determinant of T inverse, because remember the inverse and the transpose are the same thing, minus, and instead of the identity matrix, I'm going to say T inverse T. Because if you have the identity, which is the same as doing nothing to a vector, then performing some attitude transformation and then undoing that attitude transformation would accomplish the same idea. So we're allowed to make that substitution. And maybe we can do a little bit of grouping here. So this is really T inverse and then I minus T. Right? And we can split this up. The determinant of T inverse times the determinant of I minus T equals 0. But we know that the determinant of T inverse is 1. And so what can we take away from this? We know from all the way up here, tighten that up, that the determinant of T minus I is 0, and the determinant of I minus T equals 0. This, I should say these, are the characteristic equations for a matrix having an eigenvalue of 1. So what that means is we know just from these two equations that your attitude transformation matrix T must have an eigenvalue of 1. Right? That comes right out of these equations here. So what that tells us then is we're going to define a new vector here. Let E with a little hat on it, which is a unit vector, be the corresponding eigenvector. And what that tells us is that T E hat is equal to lambda E hat. But we know that our eigenvalue is 1. So T E is equal to E, which, all right, this has been a lot of math. We've had some fun, determinant math, and we've had the stack of equations, which looks a little bit intimidating. But all we've arrived at is this idea that if you take the vector E and you do T to it, it accomplishes nothing. And that's not true in general. Right? If you take any vector in general and you apply an attitude transformation matrix, then we know that it would do something. It would rotate some amount, right? That's what the attitude transformation matrix is trying to accomplish. But E is special. E is the eigenvector corresponding to the eigenvalue 1 of the matrix T. Put more simply, E, scroll down a little bit, E is the Euler axis, which can be found from T by eigendecomposition, right? So E is the Euler axis. E is the only vector for which performing a rotation, so twisting the potato about the pencil, does not change the pencil. In this case, E is the pencil. That's the idea that we're getting across. So we can put this in more mathematical terms. Thus, the eigenvector corresponding to the unity eigenvalue is the fixed axis of rotation. Okay. So you might be saying, who cares, right? We've got this E, we've got some angle theta. So how does that help us exactly? What we're going to discuss next is a little bit more practical, right? An attitude, kind of what we were getting at before, an attitude can be expressed by an Euler axis E and an Euler angle theta. Now, here's a question. E has how many degrees of freedom? And theta has how many degrees of freedom? So let's have a quick sidebar here, right? Quick sidebar. On degrees of freedom. So I'll take a volunteer who likes degrees of freedom conversations here. Or we could do the dice thing. I always like to be sadistic and roll the dice, but I think somebody's got the heart of a lion today. What do we think?
I'll do it. What's up?
All right, here we go. How many degrees of freedom does the angle vector E have? Or sorry, the Euler axis E have?
1.
Hang on. Remember, this is a 3x1 vector. So this axis could be pointed any which way, right?
Yeah, 3.
Yeah. So it doesn't just have the 1 degree for. Actually, I think we got it backwards. Theta, which is a scalar, has 1 degree of freedom.
Cool.
But the axis can be pointed any way in the world, right? So how many degrees of freedom is that?
3.
3, right? Because any orientation would then have 3 degrees of freedom. However, we could just think about it this way, right? A 3x1 vector, you could plug in any number you want for x, any number you want for y, any number you want for z. However, it's not just any vector, it is a unit vector, which means it has 3 numbers and 1 constraint. Or you can think about it physically, right? An axis can be pointed in any direction in the world, but that's not exactly 3 degrees of freedom because the amount that you twist it doesn't matter, right? So you can imagine you need some angle to describe the horizontal component that it's pointing, some angle to describe the vertical component that it's pointing, but then you can twist it however you want and it doesn't move, right? It's not a rigid body. It's only just a line floating in space. And so what that means is you've actually got 2 degrees of freedom. So a vector, 3x1 vector has 3 degrees of freedom, absolutely right. A 3x1 unit vector has 2 degrees of freedom. You can think of it as there's 3 numbers, but then they all have to be such that they satisfy the unity norm constraint, right? So x squared plus y squared plus z squared equals 1. And so 2 degrees of freedom here, 1 degree of freedom here. That means that we are in good shape. 3 degrees of freedom total. And that should give us a warm, fuzzy feeling because we know that an orientation in general has 3 degrees of freedom. So we're using 4 numbers here, right? 3 numbers in the axis, 1 number in the angle, but those 4 numbers have 3 degrees of freedom. Hopefully that causes smiles. All right, thank you for your courage in volunteering here. And then the next bit is a little bit less exciting, but it's very practical. We will now show without proof, just another equation dump incoming. We could get into this if we had more time. How to convert from your attitude transformation matrix back and forth between E and theta. So the first is, let's recover theta from T. So theta is equal to the inverse cosine of, here comes a numerator and a denominator, the trace of T minus 1 over 2, and quick sidebar, TR is the matrix trace operation, which is the same thing as just summing the elements along the main diagonal. So if you take T, you sum all the elements along the main diagonal, subtract 1 divided by 2, inverse cosine, that gives you theta. And then E is 1 over 2 sine of theta. And then here comes the vector part. T23 minus T32, T31 minus T13, T12 minus T21. And that is where, remember, that we would say that T is T11, T12, T13, T21, T22, T23, T31, T32, T33. So notice that we're using the along the axis, or along the main diagonal elements gives us theta, and then it's all the off diagonal elements give us E. Interesting that. Okay, and so then we know that we can get from, let's see here. There we are. If you wanted to get back to T, we have this equation here. T is equal to the cosine of theta times the identity matrix plus 1 minus cosine theta times E transpose minus the sine of theta times E cross. Okay, what the heck does that mean? So this is a notation that I'm introducing where A cross, let's do vectors. A cross B is the same thing as A cross B. So this is what is referred to as the cross product matrix, right? So if you take a vector and you raise it to the power x, which is really like the multiplication symbol, then what it does is it rearranges the vector into a matrix such that that matrix, which you kind of think of it this way, that matrix being multiplied by B is the same thing as the cross product of A and B. And this is accomplished like so. A cross is a skew symmetric matrix, 0, negative A3, A2, negative A1, 0, 0, positive A3, negative A2, positive A1. So it is symmetric about the diagonal, but all the elements are flipped in their sign, and then the diagonal itself is 0. So this is something that you might have seen before. You can take a vector and then turn it into a cross product matrix by just rearranging its elements like so. And that gives you this matrix E hat cross, essentially. So those equations, which I might box up in red because they're pretty important, give us the information that we need to map back and forth from an angle axis, or sorry, Euler axis, Euler angle to an attitude transformation matrix. You might be thinking to yourself, Paul, you've called this whole section angle vectors, and we have not talked about angle vectors yet. We're getting there. We're almost done. So, oh, I guess the next, I'm looking at my notes. The next point I had in my notes was this sidebar about the degrees of freedom. So we'll skip this. So you can store this information in E hat and theta using 3 numbers instead of 4. And we can do that by multiplying them to form the angle vector. The angle vector. And so I'm going to call that angle vector phi or phi or pho or thumb, depending. Phi is equal to theta e. You just multiply them together, right? And now it's very straightforward. So this is now going to be a 3 by 1. It's got 3 degrees of freedom, and it uses all 3 of those to describe the 3 degrees of freedom in a rotation. And so we can very easily recover theta. Theta is just the norm of phi. If you have an angle vector phi, we can just take the norm of it to get theta. E is what happens when you normalize phi, and that's my notation for normalize. It's the same thing as saying phi over the norm of phi. So you take phi, take the norm, and then divide it by its own norm, and now you've recovered E and theta. So it's just a more compact way of storing the information in 3 numbers instead of 4 numbers. And this phi is an angle vector. Now we can also say that T, our attitude transformation matrix, is the matrix exponential of phi cross. So if you take phi, you do this to it, you get a cross product matrix, and then you take the matrix exponential of that, you get back to T. So where exponential like this is the matrix exponential operator. This is true mathematically, and it's kind of like a, hey, gee whiz, that's neat. We're not going to use it very much. We're mostly going to rely on these equations that I've boxed in red. Those are kind of the ones that matter here. This is rarely done in practice. But can be useful for derivations. So you might see this thrown around in a textbook, but you typically won't see it thrown around in flight code. And that's basically it. So this is our angle vector, which might even get its own little box here, a little red box. There we are. Also very important. So phi is theta times E. Theta is the angle, and E is the axis. E is the pencil that we stabbed through the potato, and then theta is the amount that we twist it with our fingers. And all that information can be stored as an axis and an angle, or as an axis multiplied by an angle. That's basically it. Notice that we drop the little hat. I guess this should really get a vector notation, right? Because it's an angle vector. Let's clear that up. Vector, 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 and vector. There we go. So maybe I'll tidy that up in my notes here because that's a little bit more clear. I like to use the little top arrow when we're talking about a vector here. Great. So that is Euler axis, Euler angle, and angle vectors. And also we've been talking for about 50 minutes, 50. So I think it's time for a break. So I'm going to say break time. Back at, let's go until 6 for me, 7 for you, 7 p.m. Of course, I'll stick around if y'all have any questions. Otherwise, take a break, go to the bathroom, get a snack, get a drink of water. I'll see you in 5 minutes. All right, I think we'll start back up in a second here. Just want to do a quick vibe check. Is everybody feeling okay so far about the gimbal lock and then angle vectors? No burning questions, hopefully. Otherwise, we're on to the next thing, which is the last thing we're going to talk about today, which is quaternions. I'm going to guess that some of you, maybe most of you, have been introduced to quaternions before. You might have used them before. Some of you might be extremely familiar with them. That would be fantastic because we're going to use them quite a bit in this class. They're definitely going to come up. So, quaternions were famously discovered by the mathematician William Rowan Hamilton. Not the Hamilton from the $10 bill or the musical, but mathematician Hamilton in 1843 while crossing a stone bridge. And the idea was, this is kind of a legend, that he was so struck by the idea of quaternions. They were kind of the solution to several problems that he'd been working on at the time. And quaternions, more generally, are a type of fourth dimensional complex number. That's basically what they are. And we're not going to be getting into the pure mathematical definition of a quaternion, but Hamilton definitely was. That was what he was all about. And he was so struck by this, he didn't have a scrap of paper to write it down on, that he knelt down and actually carved an equation into the bridge, which was I squared plus j squared plus k squared equals -1, I believe was the equation. So the quaternion is going to have, instead of, a regular complex number would have one real component and one imaginary component. This has three orthogonal imaginary components and one scalar real component. So it's a fourth dimensional number, which is very challenging for the brain to kind of wrap its head around. What we're going to be doing is using these as a 4-parameter construct, which is not susceptible to attitude singularities. So they're, from a pure math standpoint, they're extremely fascinating. We're going to be using these as engineers. It's going to be a little bit simpler. So quaternions are a 4-parameter construct not susceptible to attitude singularities. So we have now 4 numbers, but 1 constraint. And that is a unity norm constraint. So the quaternions that we're going to be discussing in this class are forced to have a norm of 1, the same way that our axis has a norm of 1. So if we have 4 numbers and 1 constraint, that leaves us with 3 degrees of freedom, which should be giving us a warm and fuzzy feeling because we know that attitudes in general have 3 degrees of freedom. So for more information on quaternions, because they're absolutely fascinating from just a mathematical standpoint, for more information, see one of my favorite YouTube channels. It's called 3 Blue 1 Brown. You might have heard of them. Well, it's really just the one guy before. Yeah, 3 Blue 1 Brown on YouTube has a fantastic bit about quaternions and just a lot of fantastic mathematical concepts. Definitely changed the way I think about intermediate algebra. 3 Blue 1 Brown changed the way I thought about matrix math and linear algebra, and just phenomenal channel. Definitely check it out, especially if there's something that you think that you could learn a little bit more about. I personally learn from videos a bit more easily than I learn from reading, so you might find this as a lower, kind of a more gentle learning curve. Anyway, what we're going to be doing is looking at this. A quaternion in our class consists of a scalar term and a vector term. Okay. Now, this is where we have to be careful. Some people use Q0 for the scalar term. Others will use Q4. So you have to be careful. If somebody just says, hey, here's the quaternion that maps from the inertial frame to the spacecraft frame, here's your 4 numbers, goodbye, you have to say, wait, is the first number the scalar term or is the last number the scalar term? We have to make absolutely sure that we're clear about that. What I like to do is to just remove the ambiguity completely and just use QS for the scalar term. So this is how we're going to write it in this class. Q, and it is a vector, consists of Q scalar and Q vector. I'm just going to get its little hat there. And this is the same thing as cosine. Okay, there we go. Cosine of theta over 2. And this is E hat sine of theta over 2, where E and theta are the familiar Euler axis and Euler angle from before. That's why we decided to learn things in this order. And so if we were to write this out in vector form, this would look like this. So we have cosine of theta over 2, E1 sine of theta over 2, or I guess EX, E2 sine of theta over 2, or I guess EY, and E3 sine of theta over 2. And that's going to give us our 4x1 vector. And so you could think of this as consisting of, oh, hang on. There we go. I think OneNote is getting a little bit tired and cranky with me, which it's good that I only have one more page of notes, but I might need to restart OneNote in a second here. Yeah, that not responding thing is not causing me a lot of smiles right now. Let's see here. Okay, there we go. This is equal to this. So I'm going to break it down as QS, Q1, Q2, and Q3. There's our quaternion. Now, because, so we'll say this, a quaternion carries a unity norm constraint. That is that the norm of Q. And this is, to be clear, this is the norm of the whole Q, not the vector part of the Q. The norm of the whole Q is 1. So Q scalar squared plus Q1 squared plus Q2 squared plus Q3 squared all equals 1. Because of this, oh yeah, this is starting to get cranky on me here. I'm going to restart in a minute. Because of this, its inverse equals its conjugate. And this is going to seem a little bit weird for a second, but then it's going to hopefully turn around and make perfect sense here. So the quaternion inverse is the conjugate, which this is the conjugate operation, divided by its norm squared. But remember that the norm of the whole thing is just 1. So we have the conjugate divided by 1. And this is the same thing as Q scalar negative Q vector. Okay. And now just as a reminder, Q is entire quat, and QV is the vector part. Just a quick sidebar on that. All right, so let's make some sense of this. What are we talking about? What I'm saying is if you take the vector part and you negate it, you've now undone the rotation. That is the inverse, right? And actually, it's even easier than that. You can just negate the scalar part and it would accomplish the same thing. And you might say, well, why does that make any sense? The idea here is you're undoing the rotation. So if you set the angle theta to be negative, that undoes the rotation theta about E. Now you're doing negative theta about E. Or you can swap the axis, swap the pointing direction of the axis and say, well, instead of rotating theta about E, I'm going to rotate theta about negative E. That undoes the rotation. And so the conjugate of the quaternion is the same as undoing the quaternion, and that is what the inverse is. So it's not that the inverse equals its transpose, it's that the inverse equals its conjugate. And yes, I'm just going to write that out in words. But first, I'm going to just take a second and close OneNote and then open it back up again because it's been getting a little bit, it's been fighting me. Let's see here. Hopefully that kind of cleans things up a little bit. So, thus, an attitude quaternion can be inverted by changing the sign of its vector component. Oops, whoa, all right, got a little too close to the side. Started scrolling me up here. Let's try that again. We're just gonna say vector part. Save on characters. There we go. Good enough. And this is equivalent to rotating theta about negative E or rotating negative theta about positive E. Oops, hang on, positive E. It's the same idea either way. This is exactly what we had said before, just written out. There we go. It's also worth mentioning, that Q and negative Q express the same attitude. So I've run into this problem before where if you're running some program and you expect to get a certain quaternion and you immediately see a minus sign in the wrong place, your heart drops. You think, oh no, something's gone wrong. But then you see that all 4 minus signs are flipped. You're like, oh, never mind. We're back to where we started. If you flip the sign of all 4 elements, you're right back to where you started. And so you could think of this as equivalent to rotating negative theta about negative E, which is a double negative. So you're right back to where you started. So we had a couple other equations and then we're good to wrap up. So one can convert a quaternion into an attitude transformation matrix. I'm getting excited because this is almost the last time I have to write that all out. Such a mouthful. By, here's the equation, T is equal to Q scalar squared minus Q vector transpose Q vector. All that is a scalar, and that's multiplied by the identity matrix, minus 2 Q scalar Q vector cross product, so that gets us back to a matrix again, plus 2 Q vector transpose. And that's a matrix again. And so that takes the components of Q and rearranges them and ultimately extracts enough information to rebuild a 3x3 attitude transformation matrix. There we go. There we go. Now, just a few more fun facts about quaternions, and then we'll wrap up. We can use the quaternion multiplication operator if we have sequential rotations. But we must be careful. Of our conventions. Scroll down a bit. There we go. We use the non-Hamiltonian convention so thanks, Hamilton, but we'll take it from here, such that quaternion multiplication occurs in the same direction or the same order as matrix multiplication. Which is to say right to left. So remember that order matters when you're multiplying matrices, order matters when you're multiplying quaternions, and we're going to be working from right to left. So here's the quaternion multiplication operator. So we've got some quaternion A, and we're going to use this symbol to multiply them together, and some quaternion B. And what this is as follows. We have quaternion B scalar, quaternion A vector, plus quaternion A scalar, quaternion B vector, minus quaternion A vector crossed with quaternion B vector. And so that all of that is a 3x1, and then the bottom is a scalar. Quaternion A scalar, quaternion B scalar, minus quaternion A vector transpose quaternion B vector. And we have to be careful. This is the vector part, and this is the scalar part. And there we go. I might make a note about that in my notes just so we don't get confused. So in that equation, I just happen to have the scalar part written on the bottom, but as long as you keep your priorities straight and you make sure you don't mix up the scalar part with the vector part, we should be good to go. I recommend if you ever write a function in MATLAB or Python to pass around quaternions, you actually pass around the scalar part and the vector part as two different elements, or you create a struct, q.s and q.v, something like that. Passing it around as four numbers is asking for trouble. That's my recommendation. That's also how flight code does it at NASA. Because we've defined multiplication this way, we can say that the attitude transformation matrix created from Q B to C being multiplied by Q A to B is the same thing as the attitude transformation matrix from QB to C multiplied by the attitude transformation matrix QA to B, which is the same thing as TB to C, TA to B, right? And so what we're saying is if you take the quaternion from A to B and multiply it by the quaternion from B to C, you should get the quaternion from A to C. And so you could think about it this way. T of the quaternion from A to C can be split up like this, and this ultimately gets you the T from A to C. So actually, I'm going to add that to my notes as well. I think that's more clear. T made from the quaternion from A to C, this is equal to T A to C. So last idea, we can also represent quaternion multiplication in this way. QA multiplied by QB is the same thing as Q raised to the multiplication symbol times QB, where we're producing a quaternion multiplication matrix. So QA raised to the power of multiplied is equal to this. And so this is where we got to be careful here. Q scalar I 3 by 3 minus Q vector cross Q vector negative Q vector cross. Oh, I'm sorry, not cross. Yeah, I'm trying to undo that. Erase, please. That should be transpose. Hopefully that makes sense why. In a minute when I regain the control over my erase button. There we go. There we go. So slip of the hand should be transpose. There we go. Q vector, and then this should say Q scalar. But again, we need to be careful where we can think of this as a 3 by 3, a 3 by 1, a 1 by 3, and a 1 by 1, where this is the scalar term down here, and this is the vector term up here. So these equations, which I have here and here, you just need to be careful. These are written with the vector part first and the scalar part last. That was just kind of the original way I was taught, and I've later kind of moved on to having the scalar part first. So just, yep, I set up a landmine for you, and now I'm saying don't trip on it. But hopefully it makes sense. If you wanted to treat this as a 4 by 1 vector, you could absolutely do that. You would just move this around a little bit, and then this would move to the top left, this would move to the bottom right. Or if you feel like using scalar last, you can just go through with the equations this way. I'm going to make a note to self. Note to self. These quant equations are scalar last. And I'll fix that in my notes for next time. Anyway, somehow I had imagined that we would take about 4/5 of a normal class time because we went through only 4 pages of notes, and last class we went through 5 pages of notes. But somehow I managed to take the entire kind of allotted lecture time. So my apologies that we weren't able to finish up a little bit faster, but we got through a lot of good stuff today. We are done with attitude representations, and actually we're not that far away from starting onto some of the estimation theory mathematics, but I believe we have 1 or 2 more introductory lectures before we wrap up. So any questions about the content that we went over today? Otherwise, I'll stop the recording and I can stick around for the next half hour to talk about the homework. Good stuff. All right, I'm going to stop the recording. Thanks, everybody, but I'm not going anywhere. We're going to talk about the homework.